Okay. Good morning, students. Welcome to the first lecture, okay, of applied mathematics. Now, before starting integration, I hope you remember differentiation, right? So, basically, differentiation was centered around the concept of defining tangent lines and then finding the slope, right? But what about integration, right? Integration is defined on the center of calculating the area of the region bounded by the graph of the functions. Fine? Now suppose this is an interval. Okay? So now, if a function f is differentiable, okay, in this interval, then f dash exists at every point of I. But what about the reverse process? If f dash exists, then can we get this function back? Right? So the answer is yes, we can get the original function back, and that is through integration. Okay? So now, so basically there are 2 points. Integration is defined, right? Why is integration defined? The first point, the first problem is problem of finding a function wherever its derivative is defined. Wherever its derivative is defined. Okay? And what is the second problem? Second problem is problem of finding the area, right? I just told you the concept behind integration. This is the concept. Finding the area bounded by a region of a function. Okay? So, the first problem is of finding a function back wherever its derivative is defined. Like for example, I told you the example where a function was differentiable in a certain interval, right? And that means that the derivative will exist at every point of I. So what if the natural question arises, what if we want to find the reverse, right? If we have a derivative available, can we get the function back? Yes, and that is through integration. So this is the first problem, and this is known as indefinite integral. Indefinite integral. Okay. Now, the second problem, where you want to find the area bounded by the region of the graph of a function. I missed a point under certain conditions. integral. Here you will be getting a generalized solution, okay? There are no conditions here. There is no limit involved. But in definite, as the term definite suggests, right, you are basically defining the problem in certain limits, right? So here you have to apply limits to get the particular solution. So both A and B constitute of what we know as integral calculus. Okay? So this is what is basically integration all about. Okay? Whenever you are asked a question, what is integration, right? You have to define it like this, that integral calculus basically consists of two parts. Part A, part B, right? Part A is indefinite integral, part B is definite integral. In indefinite integral, we are basically solving problems where we are given derivative and we have to find the function, right? Related to it. And in definite integral, we are actually dealing with problems where we are finding the area bounded by a region of the graph, right? And that too under certain conditions, right? So this is what is integration all about. I hope the definition is clear. Now, you can note it down if you want, or you can pause the video to note it down. I hope you all are maintaining a separate copy, okay? That is a must, because believe me, the subject might get tougher afterwards. So if the base is not clear, you won't be able to deal with the advanced terms. So make sure you note down everything, okay? I'm rubbing it. Now, you can note down certain points, right? That how is integration connected to differentiation, and furthermore, what is the geometrical interpretation of integration? You know what? Whenever you start any topic, you need to understand that how is it basically like being used practically in life, right? Like for example, differentiation and integration all have practical implications, and you will learn that soon, because in this chapter we will be dealing with applications as well. And second part, the problem of finding the area, is basically a practical application of integration, right? So I hope you have noted it down, okay? I'm rubbing it. Now, okay. So now first point is, how is integration related to differentiation, right? So integration is the inverse process of differentiation. I hope I cleared it through the first example that I told you, right? Where we defined that function in that interval, and then we said that we can differentiate it, right? It was differentiable in that interval. So the derivative was existing at every point of I. And then what we did? We reversed it, that if we have that derivative available, can we get the original function back? We said yes, through integration. So what it implies? That integration is the inverse process of differentiation, okay? So the first point is integration is inverse process of what? Differentiation, definitely. Okay, now, for example, dx, right? We are differentiating the function which is x cube. What is the function? F of x. Why f of x I said? Because the function is in terms of one variable which is x. F of x is x cube. Now when we are differentiating it with respect to x, that is why I wrote it like this, d by dx. Okay? I'm telling you the basics in starting only. Afterwards, I don't think so I'll be covering these many minute details. So please be with me, okay? Okay. So when we are differentiating the given function x cube with respect to x, right? I hope you have studied differentiation. If you haven't, see what will happen. Do you know the answer? If we differentiate it, what we'll get? X square, right? So now, x square I'm sorry I wrote the question wrong. That is what I was thinking while filming the video. That what happened? How is it coming x square? Anyways, this is 3 comes in front. Okay, 3x 3 minus 1, and we have this 3 as well, right? Okay. This and this gets cancelled, and 3 minus 1 is 2. So x to the power 2. Fine. But similarly, d by dx of e to the power x, exponential function, it remains same. Okay. So if you understood what I did, after differentiating we got this, right? So x square is the derived function of x cubed by 3. Then what do you think x cubed by 3 is? Can you tell me the answer? Right? Then x cubed by 3 is antiderivative, right? Opposite. Antiderivative, or to make it more clear, integral. Okay? Similarly, e to the power x, right? This was the derived function. So this is the antiderivative or the integral. So proved that integration is the reverse process of, inverse process of differentiation. Okay? Okay, I'll give you 1 minute. You can note it down. Okay? I'll be sharing the formulas with you. Don't worry about that. The famous formulas, right? Like what is the, like d by dx of sin x is cos x. Then what is the integration of cos x? It's sin x, right? I hope you are not confused in that. D by dx of, what I said? D by dx of sin x is cos x. Then opposite, right? This is what I said. Then integration of cos x dx is what? Sin x. Right? You can map it, right? This is what we learned right now. But certain formulas are comparatively different, like you have to derive it in integration. So I'll be telling all those. Don't worry about that. You can just note it down. Then we move forward to the geometrical interpretation of integration. Okay? Let me note it down. Just I'll give you some seconds. Okay, I hope you wrote it down. Okay? Because there are some restrictions while filming a video. So. Okay. So we have now geometrical interpretation of integration. Now, what is a geometrical interpretation, right? Now, for example, consider a function fx equals to 2x. Okay. Now, if you integrate fx, what will you get? How do we do integration? What is the function? This, right? So x power कितनी है इसकी? 1. Power is 1. So 1 plus 1 upon same 1 plus 1, and you have 2 in multiplication. Okay. So this is 2 into x to the power 1 plus 1 is what? 2 upon 1 plus 1 is what? 2. 2 to what? Cancelled. And where is my second pen? Something got introduced, which is plus c, and this is known as the what? Constant of integration. This is not working properly. Okay. Constant of integration. Now, why I introduced constant of integration? Think about it. Like, just do the reverse process, okay? If I write constant of integration is just a constant, okay? You can replace it by 1, minus 1, minus 2, right? It doesn't matter. Now just write x square plus 1, x square plus 2, x square minus 1. Check. Differentiate it. If you differentiate it, you will get 2x plus constant का differentiation is what? 0, right? So just 2x. 2x plus 2. Differentiate it, you will get 2x. Constant का differentiation again is 0. And the third one. Differentiate x square minus 1 with respect to x, you will get 2x. Right? And again, the differentiation of minus 1 is 0. So what you got? Same answer. But again, all the functions were different, right? X square plus 1 is different, x square plus 2 was different, and similarly x square minus 1 was different, right? So this is the importance of C. All the three are different functions, okay? But when you differentiate it, you get 2x. Now, so basically, this is my point of introducing this constant of integration. I hope you get it, right? Now coming back on to the geometrical interpretation. So now, x square plus c is basically representing the family of integrals, right? X square plus 1, x square plus 2, minus 1, minus 3, whatever, okay? So this is family of integrals, right? And how are they different? They're different by this constant, right? So now, if you plot it, right? Now, when c is 0, then y is equals to x square. ठीक है? fx is y. Fine. This is a parabola, right? So how it will be represented? The center will be at 0, right? So this. Fine. Now, when c equals to 1, then y is equals to x square plus 1. Don't get confused with y, okay? I hope you are not getting confused with that, please. X square plus 1. So now, this will be at point 1, okay? So this was x square. And this will be what? X square plus 1. Fine. Similarly, if c is equals to 2, then y is x square plus 2. 2 is here. So here. So this is x square plus 2. Now, when c is positive, when c is greater than 0, then it is on the above side, right, of x-axis. When c is less than 0, then it is on the lower side of the x-axis, right? So similarly, I can just plot 1, okay? C equals to minus 1, then y is x square minus 1. Minus 1 kahan hai, huh? Minus 1, right? This will be like this. Why I am drawing a parabola, I hope that's clear, okay? This equation represents the parabola, okay? Now, just let us consider that all these parabolas you are intersecting by a line which is x equals to a. Fine. And now you have to define the tangents, right? How are we going to define it, right? By defining the slope. How are we going to define the slope? By differentiating the equations, right? So, if you have y equals to x square, x is what? So, by differentiating, what are you getting? It's 2a. Where? At y equals to x square. Similarly, if you are using this equation, y equals to x square plus 1, again it will be a square plus 1, right? 2a. Similarly, for x square plus 2, you will get 2a. For x square minus 1, this is x square minus 1, you will get 2a, right? So, what I proved? You remember the example I did? We were getting the same, right? On differentiating, you were getting 2x. What was the similarity? That the slope was similar for all the curves. But they are actually different. All these are representing a family of integrals, right? They all are differentiating by a single constant c. Okay? So, if you define the tangents, right, you will be getting slope as 2a, 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 2a. So, this is the point, right? Okay? So, geometrical interpretation is clear. We will be starting with the questions, right? And like simple questions at first. There are certain properties as well notes of those properties though. I hope you got the basic idea behind the integration. Okay, just tune back to the next video. Okay, thanks.